So now that we have the kind of the basic idea down of what's involved in differentiating something implicitly, let's take a look at some examples, right? And I'm going to go all the way back to the circle that I used to kind of start off this topic in the last lecture, and say, well, okay, how can we differentiate this? How can I figure out what y prime is, right? What the rate of change is for this function, or what's the slope of the tangent line to this function at a point? Remember, the derivative means the same thing. So I'm going to differentiate this. Differentiate the left side. This is x squared plus y squared, and differentiate the right side. So let's see, I'm just going to differentiate the parts over here on the left. The derivative of x squared is 2x, and the derivative of y squared, now remember, y is a function of x. So this is actually a chain rule situation. This is going to be, I'm going to bring the exponent down in front, use our power rule, 2y to the first, times the derivative of the inside, times the derivative of y, which is y prime. And this equals derivative of constant, that's 0. Great. Okay, so let's solve this, right? Solve it for y prime. Move the 2x over, 2y, y prime equals negative 2x, and then divide both sides by 2y. Y prime equals negative x over y. So actually a pretty simple result in the end. Okay, and let's test this out here a little bit. Now let's think about these two upper and lower points. This point here is 0, 5, and this point down here is 0, negative 5. Well, what do the tangent lines look like at these points? Well, one of them is here, right, and the other one is here. They're horizontal lines. So these are good points to test because I know what y prime should be here. If everything works out, y prime should be 0 because that's the slope of a horizontal line. Okay, well, let's try it out. Let's put those points in here. Y prime equals negative 0 over plus or minus 5, which is 0. Awesome. Exactly what we expected to get. Okay, so how about at the other kind of outer edges? How about here and here? Well, this point is 5, 0, and this one is negative 5, 0. And think about the tangent lines. The tangent lines here are going to be these lines. They're vertical here at the edges. And I know, right, the slope of a vertical line is undefined. All right, well, let's see how that checks out in our formula. Now I'm going to have y prime equals negative plus or minus 5 over 0, which is undefined. So that's awesome, right? Our new method is giving us exactly the same information that we kind of intuitively expect to get at the points where we can make reasonable predictions. Okay, so let's try another one here. Now, right now, same function, so I'm going to cheat just a little bit. We already did this. Y prime equals negative x over y. So what I'm going to do is, first be clear about the question. What's the equation of the tangent line? The tangent line, right? So I'm looking for a linear equation here. And I know to find a linear equation, I can just use my slope-intercept form. Y minus y0 equals mx minus x0. I've got the x0 and y0 here. That's 3 and 4. And I can get m. M is the slope of the tangent line, and that is my derivative. So the slope is, now you see here, what makes this different from what we've done before is now I need both the x and the y coordinate to get my answer, right? Where previously y prime was always a function of x, and just having an x was sufficient. So let's put 3 and 4 in here. This is negative 3/4. And now I'm just going to do some substitution. This is y minus 4 equals negative 3/4, x minus 3. And now it's just cleanup. Y minus 4 equals negative 3/4 x plus 9/4. Add the 4 to both sides. I'm going to make it 16/4 over here, right, do the common denominator. Y equals negative 3/4 x plus 25/4. And that's it. There's my answer. Right, there is the equation of the tangent line at the point 3, 4. Okay, so let's try another one, right? Just kind of getting some practice in here. I'm going to need multiple rules here to do this, right? So I'm going to differentiate dx of x squared y plus dx 2xy cubed equals dx of x. Right? I'm just differentiating all the parts. Okay, so over here on the left-hand side, I've got a product rule situation here. This is the derivative of x squared times y plus x squared times the derivative of y. See, that's nice. That's just dy dx. That's just going to be y prime. Plus, then over here, look, right, bring the 2 out and then apply the product rule. This is the derivative of, d dx of x times y cubed plus d dx y cubed times x. It's just our product rule equals, and I can go ahead and do that derivative. That's just 1. Okay, so over here, let's see. I get 2xy plus x squared y prime plus 2. See, the derivative of x is 1, so that part is just y to the third. Plus, and here I'm going to have, I've got y to a power. This is going to be a chain rule situation. So this is 3y squared times y prime times x equals 1. And that was just some cleanup, right? Just some algebra. I'm going to distribute the 2xy plus x squared y prime plus 2y cubed plus 6xy squared y prime equals 1. I'm going to take everything that doesn't have a prime and move it over to the left side, the right, move it from the left to the right. So this is 1 minus 2xy minus 2y cubed. And on the left side, let's factor out that y prime. Y prime times x squared plus 6x squared y. And then divide, right, to get the y prime by itself. Y prime is 1 minus 2xy minus 2y cubed over x squared plus 6x squared y. And that's it. I'm not very pretty, right? These do tend to get a little messy sometimes. But that's going to be my answer. All right, so let me give you one, right? Go ahead and see if you can take it through this one. Go ahead and pause if you like. Work through this, and then we'll do it together. Okay, so again, I'm going to differentiate both sides. dx e to the xy equals d dx y squared. Okay, so the left side. Remember when we're doing a number to a power, and that power isn't just an x. This is a chain rule situation. So this is going to be e to the xy times the derivative of xy. And this equals 2y times y prime. Okay, so this derivative here, this is going to be another product rule. So this is e to the xy d dx of x times y plus d dx of y times x equals 2y y prime. All right, so I'm going to do two things here. First, let's go ahead and divide both. Well, no, let's not. I was going to move that e to the xy over, but there's a y prime on the right side. So let's not do that just yet. This is e to the xy. The derivative of x is 1, so this first part is just y plus x y prime equals 2y y prime. Now let's distribute. This is e to the xy. Let's put the y out in front. Plus x y prime e to the xy equals 2y y prime. Now we just have to get the y prime by itself. So let's move the xy prime e to the x y over y e to the x y equals 2y y prime minus xy prime e to the xy. Okay, factor out the y prime. Y prime 2y minus x e to the xy equals y e to the xy. And then divide. Y prime is y e to the xy over 2y minus x e to the xy. And that's it. Again, a little messy, right? A little messy, but that is going to be our final answer. Okay. You remember we have that power rule, right? If y equals x to the n, then y prime equals n x to the n minus 1. When we first talked about this, I just kind of put it out there and asked you to take my word for it, right? We can derive this now. And we're going to do that using this implicit differentiation. All right, so here's how it's going to work. I'm going to start with y, let me start again, y equals x to the n. Okay, take the logarithm of both sides. Right? Doing that, I get the log of y equals the log of x to the n. Okay, now I'm going to, let's simplify this right-hand side. The log of y equals n times the log of x. Okay, good. Now, let's differentiate. We're going to have to do the left side implicitly. The derivative of the log of something is 1 over that something. So this is 1 over y times the derivative of that something. So this is y prime equals n over x. Okay, good. Now remember what have we always done here, right? Solve for y prime. Multiply both sides by y. Y prime equals ny over x. Okay, but why? Y is just x to the n. Right, so I'm going to substitute that x to the n down here for y. And this becomes y prime equals n x to the n over x. Now I'm just going to apply our exponent rules, right? When you're dividing two exponents, you subtract them. So this is y prime equals n x to the n minus 1, and that was my formula, right? Really quick and simple once we have this implicit differentiation tool to work with. Okay, so where to now? Well, really we're done with derivatives. We now know how to do the derivatives of every function that we're going to be concerned with, and we really do have a lot of them. You can differentiate any trigonometric function. You can differentiate any polynomial. You can differentiate any logarithmic or exponential function. You can differentiate our hyperbolic trig functions that we just learned about. And you can do practically any combination of them. Right? You can differentiate products and quotients and compositions and all sorts of things. So that the volume of functions that you now know how to differentiate really is pretty enormous. For practical purposes, it really covers everything that you are ever likely to see in a practical situation, unless you're doing some really weird physics or engineering stuff. So what we're going to do next, we're going from here in the next chapter, we're going to look at application of these derivatives. Right? Now that we have this tool, we're going to turn around and see what exactly it is we can do with it.